Good afternoon, ladies and gentlemen. It is my pleasure to welcome you to the third meeting of the 132nd session of the British Astronomical Association. We are meeting here today in the London Irish Centre in Camden Town, a venue that I have never been in before, and none of us have, in fact, but the Guinness is on tap here, I think. So it has that to be said for us, at least. And they've made us very welcome. So thank you very much to the staff of the London Irish Centre. Traditionally, the President welcomes any new members who are attending a meeting, or any members who have never attended a meeting before, but who are attending a meeting for the first time. But they have to own up. I have no way of actually picking you out. So would anybody like to let us know that they are a new member? And this lady over in the corner would like to tell me. No? No, they've been arrived for a while. Right. I have nobody to welcome, particularly to the association. Well, you're all equally welcome. And especially the contingent from Wolas. Yes. No shout-outs. No favouritism here. We have approved some papers at the council meeting, which took place earlier today, which I will tell you of. I'll tell you, I think the reason this happens in these meetings is if you go way back to the Victorian period, I think the whole membership voted on these papers. It was considered a really important thing, what is and what isn't published in the journal, and I think everybody at the meeting voted on them, but we don't do that anymore. Only the council votes on that, but we still announce these. And the papers that have been agreed to be published are one by Martin Moberly on the enigmatic Cicely M. Botley, 1902 to 1991, who was a rather famous and eccentric member of the BAA. Not that we're short of those kind of people. Then we've also approved a paper by Jeremy Shears, the 2021 super outburst of the dwarf nova LL Andromedae, and we have approved a paper by Mark Kidger entitled Backyard Lunar Mineral Prospection. Don't really know how you can prospect for lunar minerals from your backyard, but there's a method apparently, so we'll find out what that is. I also need to tell you what are the forthcoming meetings and events. Well, in February, we have a webinar on the 16th February, Wednesday the 16th at 1900. Eric Walker of the Highlands Astronomical Society will be telling us about all things all-sky, and this is his adventures in constructing or using all-sky cameras and what he has discovered about using them and tips on all-sky cameras. In March, there will be a meeting of the Deep Sky section, chaired by Callum Potter, and that will be online as well. That will be Saturday, March the 5th. And there will be a further webinar on March the 16th, and that will be on the history of silvering telescope mirrors. That will be Howard Banich, who's a well-known expert on the history of the telescope. That should be very interesting. And then the next physical meeting of the BAA will take place in London at the Institute of Physics in King's Cross on Wednesday, March the 30th at 17:30. But that is assuming that the problems at the Institute of Physics with their building, which has prevented us from using them lately, that is assuming that those problems are fixed by then. We hope they will be fixed, but if not, we'll have to make other arrangements. So you'll have to keep your eye on the website to make absolutely sure about what's happening with that. It's now time for me to pass on to the first speaker. Grant Privet, who was due to give a talk about variable nebula, has decided because he's vulnerable to infection that he wouldn't attend this meeting. So luckily, Nick Hewitt, former director of the Deep Sky section, has been able to step in with his somewhat shorter summary on the subject of variable nebulae. And after that, we have a talk by Nick James on the James Webb Space Telescope. So, Nick, would you like to begin?
Is that okay? Right, lovely to be here. Thank you, David. I'm sorry not to hear Grant's talk because he's very much more scientific than I am. But so this talk on variable nebulae is very much a little progress check about how the Deep Sky section are monitoring these enigmatic things. Now, for those of you who don't know anything about variable nebulae at all, they're reflection nebulae associated with young stellar objects. And the ones we're interested in are on the edge of molecular clouds. And this lovely picture, which is particularly good on the screen, a little bit blurry there, but that's the way it goes. This picture by Ian Sharp is a relative newcomer to the number of variable nebulae we're monitoring, and I'll come back to that towards the end of the talk. Oops. Now, this is where we are with the variable nebulae. Stars form out of these molecular clouds, either giant molecular clouds or small ones like the Taurus dark cloud, which is one of the nearest to us at 400 light years away. And the gravitational collapse within the dark cloud gives rise to starbirth. And in the early stages of starbirth, they can really only be studied in the infrared. And A, B, and C really show that progress, and that is not of great interest to the observational amateur. By the time we get to D, we're starting to get extremely interested because they start becoming fairly easy to observe, relatively. And what you have is a star, a central star, or a baby star, if you like, which has not really shaken off all its materials. It's still got an accretion disk around it. And it has a bipolar outflow, north and south, as part of that process. And then after a certain number of millions of years, it settles down. It's generally a very variable star at that point to become a pre-main sequence star and then joins the main sequence of stars in general. So that's where we are, and it's the T Tauri type stars of which particularly interest us, but there are one or two other types of star involved in this process. In the past, the original list was just six nebulae, of which I'll go through them quickly. Heinz Nebula, which is the first to be found by John Russell Hine, not very far from here in Regent's Park in 1852. The next one to be observed was, and noted to be variable, was the Corona Australis one, which we can't see from here, unfortunately, but it was observed from Athens in the 1860s and then studied quite a bit by Harold Knox Shaw from Helmand in Egypt. Hubble's nebula, although the easiest of the lot, was a bit later to be shown to be variable by Edwin Hubble in his relatively early days, using the 60 and the 100-inch telescopes at Mount Wilson. And he noted that that was a variable nebula. Now, the one that perhaps is the best coverage lately is not one of the easiest objects, and that's Gilbert Argens Nebula, sometimes regarded as Mr. G's nebula for obvious reasons. The actual nebula was discovered as recently as 1977 by our man, Gilbert Argens, and that's really very well monitored by our members. Mcneil's nebula, a more recent one found by J. Mcneil in 2004, and that's an interesting one because it ain't there anymore. which is a great shame, really. And then finally on this list, we have Tom's Nebula, which was in 2009, found by Jim Toms, and I'll come back to all these as we go through. Now, the best known probably is, and certainly the easiest to find, is in Monoceros, and that's Hubble's Variable Nebula, NGC 2261. The star is R Monocerotis, and it's a variable star. It's been known to be variable for quite some time. But this is a nebula that's been very well studied, both by amateurs and professionals, for over 100 years. I just put these two comparisons up. The originals are somewhat more impressive, but this is Mike Harlow's image to one side and the Hubble Space Telescope on the other. Not on the same time, but it gives very much the look of the Hubble's Variable Nebula, and I think it's quite remarkable how much detail an amateur can capture. Carl Lampland, way back at Flagstaff in Arizona, started monitoring this nebula in 1919, in fact, before Hubble really put his name to it. And it perhaps ought to be called Lampland's Variable Nebula, but Hubble's caught on. And he basically kept going till the 1950s. And once the infrared took off in a major way, we found that the professionals became much more interested in it. Also, so did David Malin, who had good views with the Anglo-Australian telescope in Australia, Siding Spring. And he went quite deep, and we don't often see this side of Hubble's Variable Nebula. This is basically the southern fan. You have to imagine this being the northern outflow, and there had been an accretion disk here, if you remember back to that early slide, and then this deep shows this fan. I'll get rattled through those. Now, the infrared side of it was important as the studies in the infrared became better and better in the 1970s and 80s. And those of you who follow the deep sky might remember that Dr. John Lightfoot, who did a lot of studies in 1980s, was our speaker at the Deep Sky Section meeting last year, 2021. And it described this in some detail, and I think that's still available if you want to know much more detail about this nebula. Now, I have had a look for the fan, and this is just a simple sort of 15-minute exposure with one of the eye telescopes, because my home network isn't quite good enough for this setup, I should say. There we are. But I did stretch this and just caught a little suggestion of a fan here. And unlike the David Malin one, which was sort of a straight fan, I thought this was a bit kinky. Since in the 4 years that have elapsed, I really haven't gone back to see whether it's still like that, but nevertheless, it's something I think I will do, having reminded myself putting this together, that it's something I meant to do. So that was Hubble's Variable Nebula, well studied by the professionals, and probably because of that, not so well studied by us. Also, the Corona Australis Nebula, which is not available to us unless by remote telescopes, has been studied by Terry Evans, who's a Welshman. Don't think he's here today, but he has a remote telescope in Moorrock in Australia, and he's got a 6-inch refractor, which he uses to capture this image. And these are two images, 2016, 2019, showing the changes within this nebula. Now, in this case, we've got two variable stars attached to it, and they the nebula, although it does change in shape, it's often changing in brightness in relation to the variable star, R Corona Australis, and to a lesser extent, T Corona Australis, which is rather fainter. Now, the one that I think has caught the attention of many observers over the years is Gilbert Argens Nebula. And this is a nebula in Cepheus, and it's basically available all year round. It's a circumpolar nebula. This is Mike Harlow's series from last year, showing how extraordinary its behavior is. This is PV Cephei here, and the nebula is going off at about 11 o'clock. In that sort of direction, and he's basically monitored it, coming and going over the last few months. That took us up to August. Now, he's been doing a remarkable series, but it basically pales into significance compared with David Boyd's marathon efforts. David has been monitoring this nebula from 2010, and this is his series from 2012 to 2016, when the nebula itself was rather fanny, if you'll pardon the expression. It's become less like a fan since, and quite an extraordinary object. David has been following it, and you can hardly see it in December of 2021, but this is how it was in 2016 before it became a streak. And David has been following it. This is the star's light curve, and it had a big dip in 2020, which was followed by a big dip in the nebula's brightness. And generally speaking, the nebula follows the brightness of the variable star. But there was a time here where it really didn't much. The star became really quite bright, well, by variable star standards, and it just didn't follow suit. But it did have this big dip and an even further dip. And it is starting to perhaps come back now. Heinz Nebula was the first to be discovered, as I mentioned, and this nebula, NGC 1555, had an extraordinary career early on, because more or less as soon as it had been discovered by Heinz, John Russell Heinz, it disappeared, and it wasn't picked up again until the turn of the century, 1900. And it needed a pretty big telescope to do that. And once it had come back to normal, people started observing it sporadically, but in fact, it wasn't doing very much. But now we've got a recent series by Richard Sargent from Cheshire, and he's using a 14-inch celestron, and certainly showing some quite marked changes. And so what is going to happen to this nebula, we're not sure. But you can see it's sort of got a couple of appendages, or you could say, or certainly brightened lobes here back in October, which have gone and faded again. So it's well worth keeping an eye on this nebula. This is in Taurus, so it's very, very well placed throughout the winter. And I think Richard's doing a grand job in following this on a pretty well monthly basis. This is his little animation showing the brightening, and the star itself is perhaps slightly variable. We know it's a variable star, T Tauri, and the nebula itself is brightening. But these lobes are becoming really very much more noticeable. Rapidly moving on, this is the one that disappeared. Mcneil's nebula was found. In fact, it had been probably spotted back in the 1960s by an American observer called Everard. But he didn't really note it, and J. Mcneil was testing his very small refractor, looking at this nebula, Messier 78 in Orion, and noticed that this nebula had popped up, and it stayed popped up and reasonably bright until November the 5th, 2018, when Mike Carlo found that it had disappeared. And he alerted the world to this disappearance, and I'm afraid Mcneil's nebula has not come back. We're looking at it fairly regularly, but it just ain't there. This is an image by Nick Szymanek showing the whole of the Messier 78 complex, and the double star is here, and there is no nebula. But in fact, what he has found, the little double star there. This is magnified, and basically you have this variable star V1647 Orionis is still just there, but the nebula is nowhere to be seen, even on a pretty deep image. More observations on a regular basis, please. Tom's nebula is not over-popular, and it's not over-exciting at the moment either. Is here, and this is Monoceros as well. It's linked to the variable star V900 Monocerotis, which is a rare star. It's an FU Orionis variable, which is one that does not have emission lines. Most of the Meteorites have marked emission lines in their spectrum. This doesn't. It basically has absorption lines and quite a bit of mass loss. This is an image that I've taken. This was This was with a remote telescope again, because this really is quite faint, and not many people are doing serial observations of it. But we now have 3 more nebulae added to this original list, which I'd like people to start doing on a regular basis if you've got so inclined. They are pretty faint, they are pretty fuzzy, but that's what we like in the deep sky section. The first is Borisov's nebula. Well, I'll mention these 2 first. Yeah, I'll pass on that for speed. I'm going to come to Borisov's nebula later, by the look of it. This is the so-called RES nebula, and it's in a beautiful little area of sky in Perseus, and it's called the RES nebula because 3 Swiss astronomers in a group called Ceres, Christian Rusch, Egon Eisenring, and Rainer Spaeny, discovered this in 2014. They'd imaged it several times, presumably just as a nice nebulosity and dark nebula to image. And basically they found that the very, very small nebula, which I'll show more clearly in a minute, is variable. And it's had a deep fade for about 2 months in 2014. Now, since then, it's come back and is not doing anything very unusual. This is a Richard Sargent one, and this is the nebula here, and that nebula pretty much disappeared in 2014. And the HBC are the 3rd catalogue of the Herbig-Bell catalogue of emission nebula stars, and there are 2 of them associated with this nebula. Now, Richard Sargent is starting to look at this in some detail. He's regularly imaging it. We haven't seen any change of late, but you just never know. V347 in Auriga is another one of interest. Richard Sargent, again, has taken this 2 images in October and November, showing a quite marked brightening of the nebula between the 2. This very much keeps in track with the star. The star is, as it gets brighter, so does the nebula. But we don't know much about the behavior of this nebula. It was only really put on the map in 2020, so it's only sort of just under 18 months old now, as far as observations are concerned. Now, finally, I think I mentioned Borisov's nebula in Cepheus. Now, Borisov's probably better known to you as discovering an interstellar comet, which was, I think it was 2I 2019. 2I, yeah, thank you. Which was quite an extraordinary discovery of this comet, which was sort of between the stars, if you like. But he's actually had 9 other cometary discoveries to his name, but was looking at this nebula also in Cepheus. Now, it's very difficult to see here because it's low contrast. It is not the most exciting fuzzy blob that you'll have ever come across. I fully appreciate that. But it was noted to become available to the optical, having been known to the infrared astronomers. So it's obviously something's going on there, so it would be nice to know what. I suspect it's got brighter and it's got more developed, and then therefore has become available to the amateur. And it may just get brighter and brighter. We have to wait and see. This, I can't quite remember when these are both Richard Sargent images. That one from, I think, August, and this one from November, which showing very, very little change. So finally, just... is docking as well. Yeah. I'll just speak up.
There's a switch on the microphone, is that on?
Push it up.
Push it up, yeah.
Nick's noisy. This is, again, yeah, I know. It's, yeah, fine. Not sure what I can do about that. This is. That's okay. No, that's okay. This is Ian Sharp's image again. And the variable nebula associated with this complex, which is a lovely little area of reflection nebulosity, and dark nebulae, there's Barnard 1 and Barnard 2 here. There's the variable nebula. Now, we don't really know, again, what's happening to that at the moment, but it has been seen to fade, and we're keen to have more observations of this nebula. So, finishing off, there are now 9 targets, so still a manageable number for people with decent-sized telescopes, but there are a couple of smaller, easy nebulae for people to have a go at. Further monitoring is still regarded as useful. John Lightfoot certainly said that monitoring the variable nebulae by amateurs was still of great importance, which was nice to hear from the professionals. I think it is possible there may be further discoveries. There have been 3 in the last couple of years, really. So there's still a hope for Hewitt's variable nebula, along with Hubble's and Heinz. I always like the idea of that. It's important to think in terms of serial observations made with the same instruments. This is David Boyd's done a marvellous job with Albertagnus Nebula, and Richard Sargent is doing extremely good work with his telescopes too. So I'd like to just thank the main contributors, including David Boyd, Terry Evans, Mike Harlow, Nick James, Grant Privet, and Richard Sargent, and I shall get more involved in this game now my telescope's up and running. Thank you very much. Questions?
Thank you very much, Nick. Does anybody have any questions for Nick?
Yeah.
Question over here.
I'll repeat the question, Nick.
I'm just wondering whether, yes, so which nebulae and what sort of focal length instruments would you need, to study the morphology, say, subtle changes in, say, Mr. G's structure, and then sort of changes in the integrated brightness of perhaps some of the bigger ones, something like that, just sort of, and possibly whether there's also standardized approaches. Obviously, David Boyd has developed one for the nebula around PV SEP.
Yeah, right. The question at the beginning was the dimensions, really, of some of the variable nebulae. And Hubble's variable nebula is probably the largest of them, and that's about 2 arc-minutes across long. And most of the others are a little bit smaller, being further away. They're pretty faint, some of them. Whether they would be any use for cometry work, I'm not entirely sure, but Nick perhaps could answer that question. I think they're just, with some of the fainter nebulae, just getting the nebula itself would be quite an achievement. I think you probably need 8-inch telescopes upwards and imaging, with the exception of Hubble's variable nebula, which is certainly, I've seen nice drawings of that. Heinz variable nebula 2 is one that can be visually picked up reasonably easily with modest telescopes. But I think if you've got something of the order of a 10-inch, 12-inch, or 14-inch telescope, forget what you use, David, it's 12-inch, isn't it? 14, you're 14-inch. Yeah. That's the sort of aperture that's starting to get the best results for this kind of work. But I think I will let you know how I get on with my 9.5-inch and my new camera. Don't tell her indoors that I've got a new camera.
It's just been broadcast live.
Yeah, but she won't watch. I'll let you know, because it's a much more modest setup, and if I can get onto some of these, it'll be good. But regards commentary side, I'm not sure if they would be terribly helpful. Yeah. far away.
Thanks very much, Nick. A fascinating presentation. Couple of points. Firstly, the light curve you put up, I noticed this is often the case with light curves, never any error bars in it. Is that because it's all taken from different observers, so there's no means of calculating it?
Well,
And secondly, perhaps more trivial, the nebulae have disappeared. Are those associated with the T Tauri stars, in which case is that to do with stellar evolution, or is there some other reason?
Well, I think the other reason is almost certainly that there's something that has obscured the star, or at least the fan part of the nebula. The one that's disappeared, Mcneil's Nebula, is an FU Uranus star again, and they don't behave quite the same way as a T Tauri, but it's in a very dusty area. It's part of the Orion complex, so it's that bit further away. It's probably about 1,500 light years away. I think what's happened is some large chunk of dark molecular cloud has probably gone in the way of the fan, so preventing it being illuminated by the star. With regards to error bars, I think just David doesn't make errors, do you, David? No. Perhaps
He will
David
have
might-
inbuilt errors and tolerances, but fine.
Okay. I rest my
That's a
case
good
with that, yes. Fine.
We've got questions from people on YouTube as well. I'll tell you, we've got 43 viewers currently on YouTube, so it's a similar number to the people in the hall. Daryl Dobbs has asked a couple of questions. He asks, is it possible that stellar winds from the illuminating star have blown away the material forming Mcneil's Nebula, or is it down to reduced output from the star?
Well, that's an extremely good question. I think it's probably not down to I don't think the star would become so dim in such a short period of time. I don't think it's got rid of its material yet, no. I don't think that's the case. I still think, because we know that there is material floating around Hubble's variable nebula, for instance, and it's a light show. It's basically clumps of stuff near the star being projected onto a bright cone of material in the outflow. I think it is probably just a large chunk of something that is preventing the star being doing that illumination. But, you know, I need to look up much more about that particular object, and it's very little in the way of papers to tell me any answers on that. I have had a look. But
Daryl also asks about infrared. Has anybody searched for these nebulae when they've disappeared in infrared?
Well, that again is something I have looked up, and it's very difficult to find papers on that. I'm sure that the infrared astronomers are looking at these, because star birth is one of the hot topics, and I'm sure they are. But in specifically to Mcneil's Nebula, I'm not aware of any papers recently. Though I might need to go back and study the literature a little harder.
It seems to be a fairly wide open field for amateurs.
I think very much so, yeah. I think it's something that we could all get involved with if you've got an interest in the deep sky and monitoring things. Let's face it, there aren't many things in the deep sky that change. So this is one that does, and could lead to great discoveries, possibly. But the infrared is probably the way forward.
Well, thanks very much, Nick. That's all we've got time for to discuss that. And another round of applause for Nick Hewitt.
Do you want to take over your...
And we will pass on to another Nick. Nick James will be well known to most of you as director of the Comet section and a former paper secretary of the BAA. And he's been drumming up interest in the James Webb Space Telescope, specifically BAA members observing it. And many people have reported on the BAA website their observations, their photographs of the James Webb Space Telescope and its various bits and pieces of that rocket that have gone into various orbits now. So I will hand over to Nick to give you the update on the James Webb Space Telescope.
Yes, so those of you who were at the Christmas meeting will remember I mentioned the James Webb right at the end of the Sky Notes, then with a great deal of trepidation, because here it is, here's the James Webb, $10 billion worth of incredibly advanced engineering that was going to be put on an Ariane 5 rocket launched from French Guiana to the second Lagrange point, the L2 point. And at the time I mentioned it at the Christmas meeting, this was before the launch, and so it was a hugely kind of scary time for the people working on this mission, really, and for every one of us who's interested in finding out what this amazing telescope is going to be able to do. As it turns out, as you all know, the launch was incredibly successful, and as an engineer, I'm astonished by how successful it's been. The amount of unfolding of this object that's had to go ahead in the last 3-4 weeks since launch is just boggles the mind, and everything has worked perfectly. So what I want to do is just talk a little bit about what the mission is, where it is at the moment, and what some of our observers have managed to do in terms of being able to image the spacecraft and the upper stage of the Ariane rocket on their way away from the Earth. So the first thing is, as I mentioned, it's going to L2. So L2 is this interesting point, which is an unstable equilibrium. So if you think of the top of a hill, that's an unstable equilibrium. If you're a marble at the top of a hill and you're right at the top of the hill, then you'll stay where you are. If you start rolling down the hill, you'll roll away. And the L2 point is actually a bit like a hill. It's actually a saddle. So it's stable in one direction, and it's unstable in the other direction. And so any spacecraft that go to L2 don't actually go to L2 itself. They go into what are called halo orbits around L2. And all the spacecraft that we've currently got at L2, and probably the most famous one we have at the moment is Gaia, the astrometry mission, have to do station-keeping maneuvers to maintain themselves at L2. And those spacecraft can do station-keeping maneuvers in both directions. They can do station-keeping towards the sun and away from the sun. So if they go slightly over the ridge, over the hill, they can fire their rockets to come back again. That's not the case with JWST. JWST is a unique L2 mission, that it can only do rocket thrusts away from the sun. And the reason for that is the sunshade that it's got. So they've had to be extremely careful not to overshoot L2, because if they overshoot L2, that's the end of the mission. The spacecraft will just drift off into a heliocentric orbit. This is what the spacecraft is. It's a big telescope, and it is a really big telescope. It's a 6.5 meter diameter aperture made up of 18 gold-plated beryllium segments. The telescope is what's called a 3-mirror anastigmat. So it has the primary, the big primary here, is an ellipsoidal primary. There is a secondary at the end of this support structure, which is a hyperbolic secondary, and it's quite small. It's only 0.74 meters, so 74 centimeters across. And then there's a tertiary mirror, which does the final field correction before it goes to the instruments behind. It's going to operate at infrared, because one of the things the telescope's most interested in seeing is seeing galaxies right at the early stages of the universe, when they're heavily redshifted. So it's wanting to look far into the infrared, and in order to look into the infrared, it needs to be really cold. And the telescopes that have been launched to L2 previously have used cryogenic cooling. So they've used some form of expendable cryogenic coolant to keep them cold. They didn't want to do that with James Webb because they wanted to have a much longer mission. So the spacecraft is actually cooled passively by this massive sunshade, 21 by 14 meter capped on aluminium-coated sunshade, which is the thing that we will essentially see from the Earth when we look at the spacecraft. It's big, 6.5 tons, about the biggest thing that Ariane could launch on that trajectory, and it's big physically as well. It just about fits into the Ariane fairing. Say it's going to be looking in the infrared from about 0.6 microns, which is the red end of the visual spectrum, right up to 28.3 microns, which is in the mid-infrared. And that's why it's got to be cooled so far. And in fact, the big infrared instrument, MIRI, the mid-infrared instrument is actually cooled even further, but again, using a closed cycle cooler, so not using expendable coolant. So this just shows you where it's going. So it's going into a halo orbit around this unstable L2 point. And how's it going to get there? Well, the first thing it's got to do is get off the surface of the Earth. And then once it's off the surface of the Earth, it takes pretty much until now, in fact until about Monday, when they're going to do the final rocket burn, to get to L2. And the thing that makes it interesting for us during this period is that with the right equipment and the right telescope, we could actually follow the spacecraft from the night of the launch all the way through to now as it moved slowly through Orion and Monoceros. And it's a big spacecraft, so it's relatively bright. So a lot of people managed to get images of this spacecraft as it moved out towards L2. So it all started on Christmas Day. I'm sure many of you interrupted Christmas lunch to watch this launch. It was a really scary thinking that, you know, in this fairing at the top of the Ariane is James Webb Space Telescope, and if anything goes wrong, that's immediately the end of the mission. The bit below the fairing is the upper stage, which I'll talk about in a minute. So this is the upper stage here. This is the main stage and the solid rockets. So the French countdown goes down in French. Unlike American countdowns at T0, they light the main engine and the solid rockets are lit about 8 seconds later. Off it goes. This being French Guiana, it's almost cloudy there pretty much all the time. One of the things that you notice compared to an American launch is there's no long-range tracking cameras that are used for Ariane launches, so you will never have seen or very rarely see close-up views of the rocket with the SRBs separating. Whereas American launches generally have high-resolution long-range cameras that track the rockets, and usually they have weather constraints that they don't launch into thick cloud like this. But the Ariane is a very robust rocket. It worked perfectly. It did exactly what it needed to do to get JWST into space. This is an animation during the period when the upper stage was firing. So this small cryogenic upper stage provides the total velocity to put JWST onto the correct trajectory to go to L2. And we had a great view from the top of the second stage as the Space Telescope was separated, moved off on a path of its own. The Ariane did a fantastic job. It delivered the spacecraft with a very precise velocity and also very precise attitude and roll rates, such that the spacecraft, what was supposed to happen is when the spacecraft separated from the Ariane, there's a thing called a brake wire that starts a timer. The spacecraft has then got a reaction control system to actually stabilize itself in flight, and it had to do that before it could deploy the solar array. It turned out that the rates imparted from the Ariane rocket when it actually released the spacecraft were so good that the spacecraft took next to no time at all to stabilize itself, which is why we were lucky enough in the video, and you'll see it in a minute, to actually see the solar array deploying whilst the spacecraft was in view of the upper stage camera. So this is the solar array here. You'll see it in a minute. Rolling out, here it comes. So this was the first part, the first important part of the sequence. The spacecraft was what's called power positive. It was actually generating electricity from the sun, charging its batteries. The fact that Ariane put it into such a perfect transfer orbit meant that the spacecraft needed to use far less propellant than they were planning. And so the lifetime now, which was constrained by propellant, is probably more like 20 years rather than 10, which is a really good thing. So this is what happened. The first thing's happening. We've seen it in real life. This is the deployment of the solar array, which is responsible for powering the spacecraft. And then there's a small high-gain antenna, which you'll see here, which deploys, and that allows high-speed communication with the ground. On the night of the launch, about the only place in the UK that seemed to be clear was the northeast of Scotland. So Dennis Brzezinski got this image. Here it is there. That's the spacecraft, the James Webb Space Telescope, when it was 130,000 kilometers from the Earth on its way to L2. And for several nights, Dennis managed to image the telescope night after night from the tropical paradise of northeast Scotland, whilst those of us in the rest of the UK languished under a lot of cloud and a lot of rain. So here's another image from Dennis. It had reached 480,000 K out. This is on the 28th, and there it is. You're going to have to get better and better at identifying really faint streaks in the images here. This is an image, I think this is Peter's. Is this your one, Peter? This is Peter Carson's image, actually, of that upper stage. So the upper stage is about 5 meters long. It's quite a lot smaller than the telescope. When the telescope separates, they're both on the same trajectory. And so what happened was the upper stage does what's called a collision avoidance maneuver. So it actually fires some of its thrusters to actually deflect it from the path that the spacecraft is on. And then very shortly after that, in any case, the JWST did what are called mid-course corrections. So they ended up being on quite different paths. But there's a big difference between the upper stage, which is this streak here, and the telescope. The telescope is being tracked very, very precisely by radio tracking from the ground. Obviously, it's being controlled. Everyone's really interested in that. The upper stage, once it's finished this job, nobody really cares about. So nobody's tracking it. Nobody really knows where it's going to end up. And so it's really useful to get astrometry from amateur astronomers who track this to actually see where this stage is going to go. And I'll talk a little bit about that later, because this stage is going to come back to the Earth again in quite a while, and it's really useful to know when it'll come back and where it'll be in the sky. Here's some of my images. It had actually finally cleared up by December the 31st, so I was outside, the telescope was outside avoiding the New Year's Eve fireworks that were going on around me. Here are two sets of images I've taken, one of the spacecraft. Here you can see the spacecraft, and at that time it was about 14th magnitude, I think, and here, much fainter, is the upper stage, which is about 16th, 17th magnitude. Now, this is David Swan's picture. There's a prize for seeing it, but it's there, isn't it? So this is an animation of the spacecraft when it was 740,000 kilometers away. So we keep showing these pictures. You've got to think, what we're doing here from our back gardens or backyards is using our telescopes to image stuff that's man-made at 750,000 kilometers at this point, which is pretty impressive going, I think. This is Tim Hames, pictured by Tim of JWST this time, so that streak. So some of these pictures are stacked on the stars, and so you see the spacecraft as a streak. Other pictures are stacked on the motion of the spacecraft, so what you see then is you see the stars as streaks and the spacecraft as a dot. So 740,000 kilometers away we are here, and then what happens is that JWST deploys its sunshade. This is just an extraordinary thing. So the sunshade is, as I said, it's aluminium-coated Kapton. It's 5 layers of very, very thin plastic, which are kept in rolls. And this animation just shows how complex it is. So it deploys essentially the 2 pallets, the sunshade pallets, and then it pulls these things out. And one of the reasons that JWST's launch was delayed several years ago is because during some ground tests of this, they managed to rip the sunshade. That didn't happen, but it's just extraordinary to think that this is going on in space. So what you have is you have this big sunshade, the size of a tennis court, 21 by 14 meters across, and it's made up of 5 layers, and you'll see in this animation in a minute how those layers are separated apart. And the idea is that once this sunshade is out, the telescope will never, ever see the sun again, at least not whilst it's operational. It won't see the sun, and it also won't see the Earth or the moon, because both of those things are significant sources of thermal radiation, which it wants to avoid. So you can see here we go, the sunshade pulling out into 5 sheets. Then it deploys this interesting little thing here. And this is all to do with balancing the torque on the spacecraft due to the solar radiation pressure that is applied to this big sunshade. So if you think of a thing called a solar sail, so a big area of reflective material, the sunlight falling on it actually exerts a pressure. And I'll come to the pressure in a minute, but the brightness of the spacecraft increased dramatically once that sunshade had been deployed, but only at particular times of the night, because essentially what you're seeing is specular reflections from different parts of that sunshade. So the spacecraft went from being something that had a fairly stable magnitude to something which had really significant brightness peaks. This is Nick Quinn's picture from Stenning on the night of the 5th of January, so the first night after the sunshade had been deployed, and the magnitude had gone back up again to brighter than magnitude 15, and it had been about 16.5. And that's because of the deployment of the sunshade. And here's a really good example. So this is Mary and Mark McIntyre's video, and I'm sorry that the screen is so bright, and it's really difficult to see. But you can actually see the spacecraft moving on here, getting brighter and fainter as it moves through the field. So that was a still showing that. And Philip Masting produced a plot from that, which showed two bright peaks and then fading away again. And what's interesting is he did some observations about a week later and offset the time and got exactly the same profile. So what we're seeing here is glints off that sunshade that occur at very particular times that are very, very dependent on exactly where you are on the Earth. And so when the spacecraft gets to L2, it'll be an interesting job for someone to predict when these glints are going to happen. It's going to be a hard thing to do, but the information will be there because we'll know where the telescope's pointing and we'll know where people are. So if someone's clever enough, if you remember the old days of iridium flares, they'll be able to predict JWST flares. They won't be as spectacular as iridium flares because they'll be a lot fainter, but they'll be something that you can look out for with a telescope. So then the next thing happened, of course, was the deployment of the optics. So the optics was folded up to fit in that Ariane fairing. You have the secondary mirror support structure, so this is that 0.74 meter secondary, and then the sides of the primary mirror getting folded out. And all of that went without a hitch. All of that, hundreds, thousands of actuations of things, went without a single hitch. Quite extraordinary. So I mentioned about solar radiation pressure. So solar radiation pressure is the pressure that's exerted on an object simply due to light. So it's the photons recoiling from an object when they're reflected. And you can work out what the solar radiation pressure on a perfectly reflective mirror is at the Earth's distance from the sun. And it is, and I'm not sure whether this will mean much to you, it's 9.1 micronewtons per square meter. So that's 9.1 micropascals. The atmospheric pressure on the surface of the Earth is 100,000 pascals, so 10 to the 5 pascals. 9.1 micropascals is 10 to the minus 5. So the solar radiation pressure at the Earth's orbit is 1/10 billionth of the atmospheric pressure at the Earth's surface. So it's not much. But when you've got a big mirror, like JWST has, it actually has a significant effect on the motion of the spacecraft. An effect in two ways. One of them is that the total solar radiation force on this sunshade doesn't go through the center of mass of the spacecraft. What that means is that the spacecraft is continually feeling a torque that's trying to turn it around. And that's a really bad thing because you need ultimately to use thrusters to counteract that. So that thing you saw deploying at the same side of as the sunshade over here is effectively a mirror that is used there to balance the solar radiation pressure such that ideally the solar radiation pressure vector goes through the center of mass. So that's the first thing. The second thing is that the solar radiation pressure does have an observable effect on the motion of the spacecraft. So between the second mission, the second burn, which they did shortly after launch, and the third one that's going to take place on Monday to put it into L2, the spacecraft was just moving under the gravitational effect of the Earth and the Sun and the Moon. But if you didn't take into account the solar radiation pressure, you got quite large errors. And just to illustrate that, this is some astrometry that we've done, UK astronomers from different stations, showing the error that you get in arc seconds by fitting an orbit. This is using a piece of software by Bill Gray called Find Orb. So this is without the solar radiation pressure effect, and the errors are up to about 6 arc seconds by now. If you actually include solar radiation pressure, you can get those errors right back down again, and you can get an estimate for what's called the AMR, the area to mass ratio of the spacecraft, and that estimate is really close to what NASA predicted it would be for JWST. So a really interesting thing you can get out of amateur astrometry of this object. So that upper stage is still there. It's much further away than the spacecraft is now because the spacecraft was directed to go towards this unstable equilibrium point at L2. So it's kind of oscillating around that point, whereas the upper stage wasn't. So what's happening to the upper stage is going off into a heliocentric orbit, an orbit around the Sun. This is an image I took of it on the 12th of January, I think, by which time it was about 19th magnitude, so it's getting quite faint. But it was about 1.5 million kilometers away at that time. And then I managed to get it a couple of days ago with it 1.8 million kilometers away, down at magnitude 19.3. It's that object there, whereas the spacecraft on that night at the time I saw it was about 16.5. So the spacecraft is getting really close to the point where it gets injected into the L2 halo now. I believe the final mission correction, the correction burn is going to be on Monday to put it into the L2 halo. The spent upper stage, though, is just going off into a heliocentric orbit. And the only information we have about where it's going is coming from the optical astrometry that people have collected, because there's no radio tracking of this thing. If you take the orbit if you take that astrometry and you then put it into an orbit and you integrate that orbit forward, you get this. And this is a plot of the distance of that stage from the Earth. And you can see that it goes away to about 2 AU when it's on the other side of the Sun, then it comes back again. And in fact, in the summer of 2047, sometime in June 2047, that stage will come back to the vicinity of the Earth. It'll become brighter than 20th magnitude again for a couple of weeks, and it will probably be discovered by some neo-asteroid survey. So one of the nice things about doing astrometry on this stage is it actually will tell us, or will tell them in 2047, that no, this isn't a strange NEO sent by some aliens somewhere. It's actually an upper stage that launched JWST. So I think that's pretty good. So we want to try and follow this stage as far as we can. It'll probably be above 20th magnitude until middle of February or so, and that's something that advanced amateurs can do astrometry on. So the more astrometry we can get on that stage over the next few weeks, the more accurately we'll be able to assess the effects of solar radiation pressure on that stage, and the more accurately we'll be able to work out where it'll be when it comes back in 2047. So finally, as I say, as an engineer, I've just found it absolutely extraordinary that this mission has performed as well as it has. It's now got to the point where it's deployed all of the main mirror segments out, and they're starting a very long period of very precise collimation of those individual mirror segments into a single 6.5 meter, 1/8 wave infrared telescope. The NASA blog on this has been absolutely brilliant. It's a really good place to go for information on what's been happening. It's got click-throughs to a lot more technical info if you're into sort of really geeky stuff about wanting to know exactly what's happening with it. So I'd certainly recommend going there. The update rates on it are much lower now because all of the really kind of exciting stuff is behind us, and it's now the long slog of actually getting this telescope collimated. But if you just Google NASA Webb blog, it'll take you there, and it's definitely worth a read. So yes, I think it's just been an extraordinary thing so far. Sometime this summer we'll get the first images from this telescope, and they will just be amazing. Because of the sunshade and because of the size of it, we'll be able to follow it with our telescopes for all the time it's at L2. So that's, for a long time into the future. So we'll be able to look at the telescope that is looking at the beginning of the universe, which I think is a really neat thing for us to do. So thanks very much. I'm much happier about this now than I was in December when I mentioned it the first time. The stress of the launch is behind, and really now everything just seems to be going fantastically well. Thank you very much.
Thank you very much, Nick. We haven't really got any time, but I'll just put quickly a couple of questions that have been asked on the YouTube stream. Steve Brown asks, is there a risk to the JWST from dust and meteoroids at the L2 point? And Stephen Byth asks, does the moon ever eclipse the JWST?
So in terms of a risk from meteoroids, there's always a risk from meteoroids of any spacecraft in space, but L2 is relatively quiet. It's certainly a much less risky place to be than where Hubble Space Telescope is in low Earth orbit, because there's a lot of material there, not so much at L2. And no, the moon never eclipses JWST, because JWST is about 1.5 million kilometers away at L2, and the moon's about 400,000 kilometers away. So the moon is much closer to us than JWST is. Was the question, does the moon ever eclipse JWST? Possibly. The halo orbit takes it quite a long way out of the ecliptic plane and then back through the ecliptic plane and back again. So yes, there'll be periods when the moon could be very close, yeah.
Well, we better get on with the tea break now, so if you've got any questions in the hall, you can ask them to Nick directly. There will be tea and biscuits, I think, even served at the back. We will recommence at 1600 UTC in about 25 minutes. See you then. Welcome back, ladies and gentlemen, welcome to the second half of this British Astronomical Association meeting. If you're watching on YouTube, online, good that you could join us, and I'd just like to emphasize that if you're not in the BAA, do consider joining. You'll get full access to the website then, and you'd receive our journal, which is an authoritative publication on all aspects of astronomy performed by amateurs and related subjects like telescopes and the history of astronomy. And you can get that either sent to you printed, or you can become a digital member and just receive the publications as PDFs, which may be more convenient if you live in a distant part of the world. And you can join the BAA wherever in the world you live. So, in the second half of the meeting, we have a talk from Peter Meadows on great sunspot groups, and after that we have Mary McIntyre, who will be covering recent observations by members of the association and giving us a few pointers as to what to look for in the sky in the coming weeks. Peter Meadows is a member of our solar section, deputy director of the solar section, and great expert. He's been observing the sun for decades, and he is going to tell us about the greatest sunspot groups. I presume that means the greatest of recorded history. The biggest ones. Are the greatest ones necessarily the biggest, or can you have a great sunspot that's not that big but is great in other ways? We will find out. Peter Meadows.
One, two, three? Okay. Well, in fact, David, in this talk, we're going to talk about the largest in terms of area, in terms of the great sunspots. And I'm going to talk about 7 groups, or the Magnificent 7 for solar observers. So this particular project started about 2 or 3 years ago, when the sun was at minimum. So there wasn't anything to observe very much. So I started thinking about, well, we had some great sunspots. Most astronomers, most solar observers will know that there was a very large sunspot in 1947, which is on the image here, in April 1947, so just coming up almost to 75 years ago. So, but if you look in textbooks or in journals and magazines and indeed online, you may find the odd image, but you don't really get the history of how the sunspot group evolved and what happened on successive rotations. So I started looking into that particular topic. So that's what this talk is all about, the largest recorded groups. So here they are. So as you can see, the largest one at the top, 1947 April. Now, sunspot areas are measured in what's referred to as millionths of the sun's visible hemisphere. So the hemisphere of the sun that you see is split up into 1 million parts, and you count how many the area of the sun occupies. So you can see that the largest sunspot group, 6,000, just over 6,000 millionths, which equates to, 1,000 millionths equates to 0.1%, and obviously 6,000 is 0.6% of the surface area. That includes foreshortening towards the limb. It's for a naked eye sunspot, that's generally considered to be around 500 millionths, if you observe that with your protecting naked eye using a suitable filter. So so you can see straight away the largest ones all occurred within a relatively short period of time, just over 5.5 years in the late 40s and 1951. The 6th one is more recent, 2014, and then there was the 7th one is 1989. So let's have a look at the ones in the 1940s and the early 50s and when they occurred in relation to the sunspot cycle at the time. So this is cycle 18, which peaked, as I say, in the late 40s. The blue dots are the monthly average sunspot number. The red curve is the smoothed curve. So, in fact, cycle 18 was the third largest of the 20th century, after the 19th in the 1950s and cycle 21 in the late 70s, when I started observing. But you can see from the vertical lines, these are the dates of when these groups occurred. And you can see that the 4 ones here all occurred on the rising edge of the sunspot cycle, and you had one on the tailing, declining phase. That's actually quite unusual to get large sunspots on the rising and towards the peak of the cycle. Most of them occur on the tailing side. This histogram here shows all groups larger than 1,000 millionths relative to the peak of their respective sunspot cycle. So 0 is at the peak of the cycle. And it turns out that 2/3 of large sunspot groups occur after maximum and just 1/3 before. So these were quite unusual in appearing quite early on. As you can see, the first 2 occurred only halfway from minimum to maximum. So yes, the 1 in 89 occurred at maximum, and I'm sure there's people in the audience who probably remember that particular sunspot group and the effect it had, which I'll talk about later. And the one in 2014 is at the start of the declining phase of the group, of the cycle. So in this talk, I've used professional and amateur observations. So just to start with, talk about the 3 different professional observatories that's produced, and in case of 2 of them, they still produce sunspot drawings. So the first one is Mount Wilson Observatory near Los Angeles, and they have a 150-foot solar observatory. So the observatory itself is at the top of this tower. So there's a lift that goes up to the top. And if you ever look on YouTube, you can find a nice video of someone using this piece of equipment. And they produce a sunspot drawing 40 centimeters wide, and it just covers latitudes minus 40 to plus 40 or 30 or so. And the current person that does it, Steve, he is retired. I think he's been retired about 10 years, but he still observes. And that's true for most solar observers. They just so keen, they do it in their retirement and beyond. So the second, so these drawings have been available since 1917, so over 100 years. They also produce, for each sunspot area, they determine the magnetic field polarity of the sunspots as well. So this is quite a recent one. I'm sure Mary will say later on, activity has increased the last couple of months. The second one is a Japanese observer, Ishiko Kayama. I'll refer to it as her as HK. So she worked in Tokyo and used a 20 centimeter refractor and produced drawings of 30 centimeters in diameter. She started in 1947, so just at the beginning of the period for this talk, and she continued until 1991, even though she retired 10 years earlier. There's a theme in terms of retiring. So fortunately for both Mount Wilson and HK, the drawings are available online, which is great. And she produced some 10,000 drawings over a period of, 45 years or so. So that's a large number of drawings. And the image on the right is an example of the one from 1989. And the third observatory I want to mention is at Locarno in Switzerland. So they've been producing observations since 1957, and they were the main source of the Wolf sunspot number, which is now known as the International Sunspot number, when it was taken over in 1981 by the observatory in Brussels. So they still have the reference telescope for the sunspot number, which is an 80mm refractor. But since 1981, they've used a larger telescope to do some disk drawings. And again, the image on the right is from 1989. So you can see from the image here, it's in a nice location in the Swiss Alps. Okay, so let's start with the first one. So in this talk, I'm just doing them by date order, but the first 5 are the largest ones anyhow. So, okay, so the way I've shown the evolution of the sunspot groups is to cut out a small segment of the drawing, and irrespective of the source, they have the same scale. And it's approximately 30 degrees in longitude when the sunspot's at the central meridian, by about 25 degrees in latitude. And the rotation axis in all of these diagrams is the rotation axis is vertical, as you can see here, vertical, and east is towards the right and west is towards the left, as you would if you project the image of the sun. So the first sign of something large was at the end of January. There wasn't anything in that location on the previous rotation. And as you can see, as the sunspot comes around the limb, it evolves quite nicely. The following sunspot is the larger one of the two. There's plenty of umbra within the sunspot group. I've included a photograph from Mount Wilson. So all these are Mount Wilson. So one of the interesting things with the photographs from that period is that the umbra always seems to be overexposed compared to the sunspot drawings. So the drawings, in my view, at that period tend to be much more accurate representation of the sunspot. So one thing is you can see that on some occasion the drawing isn't as detailed. So for example here. But you can see that as the sunspot group moves across the disk of the sun, it's the following group that's the most prominent. And then it goes around the limb on the 12th of February. So these are some drawings taken by a BAA member, Dr. Ellison, who, as we were in the Ivy Centre, became the director of Dunsink Observatory near Dublin. But he's produced some very fine drawings, which are in the BAA journal. And in fact, in some cases, these are more detailed drawings than from Mount Wilson. But again, it shows the same evolution as the sunspot group moves across the disk. And there's a couple of photos here. So a photo from Mount Wilson and one from the Royal Observatory in Greenwich of the full disk. But so if you look at the full disk, you can see you've got this large sunspot, but you don't have much else. And that's what tends to happen, is that you might think at the time of these great sunspots, then there was lots of sunspot groups, but in fact, usually it's not the case. There's a couple of other images. So, although I'm concentrating mainly on white light, I have included here a Mount Wilson hydrogen alpha image with a really large flare going on at the time. So the white area is the flare. That would be very impressive to observe that. So, okay, the sunspot group went around the limb. So what happened when it came back? And so you can see as the sunspot group evolves around, just showing these roughly every 2 days, you can see that it was still quite an impressive sunspot group. But then as it went towards the limb, it started to get smaller. And then on the next rotation, it was much smaller again. So it decayed. There was a meeting in February 46 where Mr. Newton from RGO, it obviously at that time there appeared that quite a lot of professional astronomers took part in BAA meetings. And it's quite interesting in his comment. So he refers to, no doubt, that a notable specimen has been added to the bag of sunspot collector. I never thought of myself as a sunspot collector, but you can understand what he's saying. But he does then go on to say that you may have to wait another 50 or 100 years before seeing the appearance of such a large group again. But then fortunately, he qualifies the statements by saying perhaps it is unwise to predict in such matters, which in fact was the case because you only had to wait 4 months for the next one, which is this one. So back in July. And again, it was only when the sunspot group came around the limb that you could see that it was a large group. And this one was extremely complex, as you can see. There's a lot of umbra, penumbra, and it's this type of group that potentially leads to lots of flares. So again, it's Mount Wilson photo and then Mount Wilson drawings. And here's some other images. So Mount Wilson image here, very detailed. And this here was taken by a BAA member, Mr. Harris, using an 8-inch refractor stock down to a 1.5-inch telescope, which, considering the state of photographic emulsion at that time, is actually quite an impressive image. You know, it matches quite well with the Mount Wilson one taken a couple of days earlier. And as you might expect for such a complex group, there was a lot of activity in hydrogen alpha, flares, as you can see here and here, filaments. So quite impressive. And then on the next rotation, it was reduced in size, as you can see, but still, even this group here will still be visible with the protecting naked eye. So still a reasonably respectable group. So what we can do then is on the left-hand side, I've just plotted out the area of the group from February and July. And so, as I said, both of these groups started off the first occurrence occurred off very large, and then got reduced area, and then reduced area again, and the same in July. One thing you can do is, which is what I've done, is I've taken the drawings and measured the position of the main sunspot in blue, and the longitude extent of the group in green, the green line. For the 3 rotations in March, April, and then in July. And you can see immediately that appears to be a correlation between the 2 groups. That there's a constant shift in longitude. So this shift in longitude is made up of 2 components. One of them is the differential rotation of the Sun. As we know, the Sun isn't a solid body, so depending on your latitude, the rotation rate will drift with respect to the Carrington longitude rate, which is based on a latitude of around 17 degrees. And also proper motion, so the groups do move with respect to the photosphere. So if you join these up and then use the black line, for these groups, there was a differential rotation of around about a proper motion of around 7 degrees per rotation, which is quite large. And again, there was a comment in the journal linking these 2 groups up. So they also realised that they are probably from the same area of the photosphere. So just to quickly show how I can measure the position and the longitude of the group. So this is an example of a Mount Wilson drawing. When you download it, it's quite faint, so you need to increase the contrast. As I mentioned earlier, it only goes from -30 to +30 degrees, so you need to put a disk around it, and then I can just feed it into the Helio software that I wrote a long time ago now, and then just measure off the longitude of the group, and also you can measure the lat long of the main sunspots if you wish. So in a sense, you know, we're bringing these old drawings back to life and doing something useful with them. Okay, so 1947, and this time the first occurrence of the first great sunspot just appeared as a small collection of sunspots. And then as they progressed across the disk, they evolved into a much more complex group. There's no obvious leader or follower in this occasion. And then as it rotates round. But then on the next rotation, the group comes back, and this time it's much larger. Again, it's still a complex group, so just one main sunspot with lots of umbra. So here we've got a mixture of Mount Wilson drawings and ones from HK. And you can see in some cases the HK drawings have got a lot more detail in them. Must have taken a long time to draw. Lots of patience. I'm sure it's cloudy in Tokyo as well as everywhere else at times. But they're fine drawings. And these are some Mount Wilson photographs this time. So the image on the right you may see in textbooks. So Patrick Moore did a book And it shows these combination of the evolution of the group as it progressed across the disk. But again, you can see that the umbras tend to be overexposed compared to the drawings. The north and south here refers to the north and south magnetic field as determined at Mount Wilson. So again, a complex group. Okay, then next month, the sunspot group comes around again, and it's still very complicated. It tends to split, so into two parts, as you can see here. Again, the follower group is larger, far more complicated, and then it evolves and it moves off the disk in April. So it was around this time here that the largest group occurred. And again, there's some nice photographs from Mount Wilson, and again, the evolution across the disk. Again, you can see there wasn't much else on the disk apart from the main group. I've added a couple of BAA observations. So the one on the left is a hydrogen alpha drawing by Dr. Ellison again. So again, you can see some nice filaments, prominences. So the disk is actually quite busy, and a lot to see at that time. And on the right, there's a drawing from Richard Bohm, again at the time of at about the time when the sunspot group was at its maximum area. So again, a nice drawing. And then on the next rotation, the sunspot had reduced quite considerably, so not too much to see. So again, on these 4 rotations, so as I said, it started off quite small, evolved, and the blue line then evolved a bit more. So it took 2 rotations to attain its maximum area, and then decayed quite rapidly on the 4th rotation. And we can do the same as before, have a look at the evolution in longitude, and you can see that it probably appears that the first rotation is only loosely linked with the next 3. So if you backtrack this black line to this time period here, this is what you will see. So ideally the group will be here, but you can see it's adjacent to this other group. So there's not much in the way of proper motion for these groups. And if we move on to 1951, and again, this particular group evolved a bit more slowly. So it was seen on this rotation first. Again, a very complicated group. And then it appeared to sort of decay a little bit as it progressed towards the limb. But it was really on the next rotation when it came round that it evolved into its maximum area. And so you can see that, again, the group was primarily comprised just of one main sunspot, a few adjacent sunspots. Again, I'm sure magnetically it was very complicated. This is a fine photograph from Mount Wilson, which actually is in the BAA Lantern collection, which is worthwhile perusing for some old photos of sunspots and all sorts of things, comets and eclipses. Then on the next rotation, it is reduced quite down. Okay, so as I mentioned, this particular group started off fairly modest, then on the next rotation increased, and then the final rotation was much lower. And if you look at the longitude, again, there's no particular proper motion of the group. As you can see, there's virtually no change because it's a fairly low latitude sunspot. Okay, let's go on to a bit more recent times. March 1989. So back in February, there was a group seen with a nice bipolar group, again with the follower being the larger one. So this one here includes the first drawings from Locarno, just to try to fill in the time gaps of a couple of days. And then for the main group, you can see this, it came round. Now this group was at a high latitude, so it was about 33 degrees latitude, which is very high for even small sunspots, but for a particularly large sunspot, it's very unusual. And this particular cycle seemed to have a large number of high latitude sunspots, many of which were quite large. But the consequence of being at a large latitude is you get obviously the difference in the rotation rate at the bottom of the group is different from at the top. And so the group gets spread out in longitude just due to the difference in differential rotation. And that's what you can see is happening here. As it progresses across the disk, it becomes far more elongated as it progresses towards the limb. So this is on the top is a fine series of photographs from the National Solar Observatory in the US. On most days, there's a couple of days missing, but again, it shows the evolution of the group. And the one at the bottom shows the polarity, positive being white and negative being black. So again, you can see there's very complicated magnetic structure. And some images from Eric Strack. I'm sure many people in the room will remember Eric. So he did some fine drawings of the whole disk as it evolved, and a particular individual drawing here. And in hydrogen alpha, some very active prominences, and some flares, some quite big flares as well. And Harold Hill, I'm sure people remember Harold Hill as well, so he's fine drawings as well that he made. But perhaps most people might remember it for the active aurora that occurred at the time. Does anyone remember that? A few hands, yeah. So I think it even made the national news. So it was very active. So this is just an image. 1989, obviously. This is from the Astronomer magazine, which is in black and white in those days. And then on the next rotation, the group was much more reduced again. So again, if we look at the similar plots, started off modestly reduced a bit, and then on the next rotation, much larger, and then the third rotation, much smaller. And obviously, because we were at a high latitude, the proper motion is around 5 degrees per rotation of the sun. Okay, a bit more recent times, and it's interesting as you're going through these to see the evolution of amateur technology. So on the first rotation, end of September, the group was seen, not particularly big, but it was still seen. But it was on the next rotation in October that the spot evolved. It's curious why, for all these large sunspot groups, it tends to be the follower that seems to be the largest. So yes, so this was the time here of the period, October, end of October. And I've added, I'm hoping we might be able to see a movie. Doesn't look like it's going to appear. Okay, anyway, I've got some observations. The first few here taken by myself. So I primarily do disk drawings and occasionally some photographs. So again, this shows the evolution of the group. east and west are flipped on this one. But again, you can see, even with a fairly modest telescope, you can get some nice images out. And using the PST, I just managed to catch a fairly large flare, X2 flare, in the afternoon. It must have been a weekend, but the sun was getting a bit low by the end of the observation. And of course, you can pick up flares using VLF receivers from the radio section of the BAA. So some nice flares were picked up from that as well. Some more white light images. So Pete Lawrence made a series of images, again, very nice, that he provided to the solar section. Andy Davey in Hydrogen Alpha picked up I think the same flare. No, it wasn't the same flare. Other flares. So it was a very active group. Ron Johnson, I couldn't resist putting yours in, Nick, in the eclipse, and Dennis as well. So you can see that these, at this period, these photographs are comparable to the ones that Mount Wilson made back in the 40s and 50s. And particularly like this one, Mick Jenkins. So you've got a white light on the left and hydrogen alpha on the right. And so I think it's really interesting if they're, the two types of image are taken almost at the same time, you can see the differences, and you can see the far more structure that you can see in the hydrogen alpha within the group in terms of filaments and flares. And then on the next rotation, it was seen again at a reduced size. Okay, again, so this group started off fairly low, and then increased in area for the second rotation, and then low again for the third. And there's not any particular proper motion in this group. Okay, so just to finish, so I think for solar observers in particular, it's very interesting to see how these groups evolve over time, how they change from day to day, and we're lucky that all these, particularly the disk drawings, are available online, that we can do that. Now, I've used the Greenwich area catalogue and successor catalogues to determine which are the largest groups. So that catalogue began in 1874, but surely there must have been other great sunspots before then, and that might be an interesting area of research. So thank you very much.
Thank you very much, Peter. Well, some people in the chat on the internet have been asking, what do you think the prospects of a really big sunspot group for this solar cycle is?
It's very difficult to predict, but I mean, cycle 25 seems to be, the last couple of months has been progressing quite nicely. The predictions are that it might be around the same strength as the previous cycle or a bit higher. So we had one great sunspot group from the last cycle, so maybe we'll get one from this one.
It seems like this cycle is outperforming predictions. There was talk of a general quietening down of the sun about 5 years ago, wasn't there?
There was, that's right, yes. People were predicting we were going to go for a new Maunder minimum, but it doesn't appear that's going to be the case. So we might get a nice cycle.
Any questions from the hall? Yes, John Rogers.
I'll just shout. That large sunspot in 1989 March, was that the one that emitted a huge flare that blacked out Quebec?
It is, indeed, exactly the same one, yes.
Yeah. And are there usually a lot of flares and aurorae associated with the largest sunspots?
Yes. I mean, for the ones in the 1940s, there are lots of reports of flare activity, blackouts, Yes, yeah, indeed. It's because they're so complicated. The magnetic fields gets all intertwined and flares produce. So they are very active in flares. So these great sunspots are not only great in the white light, but they're great in hydrogen alpha and all the effects that they produce in terms of aurora and other effects.
There's a question here from your colleague Lynn Smith, actually. Sunspot groups 14851 of March 47 and 5395 of March 89 look very much like the famous Carrington configuration. Was there any white light flares from those spots, do you know?
Yes, there were. Yes, I just haven't included them. The main emphasis of the talk was the white light activity, but yes, there were lots of flares, and there are papers that describe the flares from Mount Wilson, for example.
And Darryl Dobbs asks about calcium K imaging. Have the spots you featured, have they been observed in calcium K light?
Well, the one for the 2014 sunspot group, yes. There were a lot of amateur observations in calcium line. And going back to the ones in the 1940s, they also observed in calcium, the professional astronomers as well, and they saw a lot of activity in calcium lines, as well as hydrogen alpha.
Amateurs are able to observe in quite a lot of these narrow wave bands now.
Yes, that's right, yes.
These days. One of our members, Gary Palmer, has been, I've seen his postings recently on Facebook where he's got a gadget which rotates different filters in the optical train of the telescope, so you can swap from a hydrogen alpha filter and a calcium K and maybe other types as well. So
yes,
it's getting very, there's a lot of equipment you can get
there. As I mentioned earlier, trying to get the different wavelength images with a short time period between them is really useful to see what's going on, especially when it comes to flares.
Yeah. Any other points? Nick?
Just about the daily drawings, daily solar drawings from Mount Wilson. Are they still going on? Because I remember watching that YouTube video you mentioned, and don't they have to climb up the tower and uncap the heliostat at the top? And
yes,
all
that's
this
right. Yes, the one I showed at the beginning from Mount Wilson was only acquired a few days ago, so it's still being done.
It's good. Yeah.
Which is great, to have the long period, over 100 years.
Yeah, that's right. It's kind of
obviously, there have been lots of different observers over that period. And it's interesting looking at the drawings. I can't remember which one it was now, but one of the groups where there was quite a few different observers over the 2 weeks.
So are they kind of amateur observers that they get to do those, or are they people up at the observatory?
Well, I think now, obviously, he's retired, but obviously still, I think he's still employed by or associated with the university.
Certainly worth watching the YouTube video if anyone
Yes.
wants to see it. It's extreme observing.
Yeah, and we're always very welcoming of drawings.
Yes.
It's lovely to see drawings and people carrying on that art and tradition and skill of making drawings of the sun and other objects, and it's always useful to have these as a point of comparison with the historical record.
Yeah, I mean, I think in terms of spacecraft imaging, the Solar Dynamics Observatory beats amateurs' disk drawings, but that's only been going for a relatively short period of time. Even SOHO images are probably only comparable to disk drawings. So yeah, it's only relatively recently that technology is probably trying to beat disk drawings. So they are a valuable resource, and it's great to have them around.
Good. Well, that's a very interesting trawl through the archives.
Yes.
And we look forward and hope that this Sunspot cycle will produce some memorable and spectacular things, and we'll keep an eye out.
We certainly will, yes.
Thank you very much, Peter.
You're welcome.
next gives me a great pleasure to introduce a lady who was at the last meeting actually receiving an award from me. She was awarded a Sir Patrick Moore Prize for her outreach work, talking to many different societies and groups, and she's got a blog and a YouTube channel all about astroimaging, Mary McIntyre. And we're very pleased that she's been able to come today to give us the lowdown on what we can expect to see in the sky in the next few weeks. So please welcome Mary.
Oh, I've got the graveyard shift again. But there are some incredible observations that I'm going to be sharing with you during today's Sky Notes, and I'm going to point out a few things that you can look for yourself as well. I'm going to start with the sun, as this is not my photograph, I wish it was. But I think you've just learned from the last talk how important it is to do regular solar observing and recording of just sunspot groups, flares, prominences, all of that type of thing. Now, we're well into solar cycle 25. It seems like it's been so long coming for it to kind of be really active. But we've had some really beautiful active regions recently. So on the 14th of December, these 3 regions rotated, and unfortunately they were gone before Christmas, but I think I was clouded out then anyway. But they were beautiful. So these pictures are by Philippe Tosi, and again, showing the side-by-side comparison of hydrogen alpha versus white light. I think it's a bit of a misconception that white light solar stuff is a bit stagnant and not as dynamic, because as you saw from those drawings in the previous talk, sunspots evolve and change constantly, and it may not do it over as short a period of time as you see in hydrogen alpha. But what you're looking at in hydrogen alpha images is that kind of the chromosphere of the sun, the sun's atmosphere. So you get all of this beautiful kind of swirling gas, essentially, and the bright plages here, and sometimes you can pick up flares amongst that as well. And just putting the two side by side, I think, is really interesting. But white light is still good as well, because if you've got a good setup, you can get these things called faculae. They're closely connected to what's going on up in the chromosphere, and you can see granulation as well. I remember when I first started solar imaging, I'm like, my images are so noisy. But no, that is granulation. And actually, if you do a really magnified view of that and time-lapse it, you can see the solar surface bubbling away. Just all of these huge convection cells. So these regions were absolutely stunning. This picture, again, by Philippe Tosi, close-up of that the day after on the 17th of December, and this is just so beautiful. I could look at this all day, I really could, and I do when I got my PST. This is from Stuart Green in Lancashire, my hometown, so hi Stuart. This is another beautiful white light image of those same active regions as they were kind of working their way across the disk. And again, loads of faculae visible here, these really bright kind of worm-like structures and loads of granulation. And actually, if you've got a really active sunspot, you can sometimes see some of that magnetic field shape within the granulation. And very occasionally, a white light flare will peep through. I've definitely done that myself, where you just get this little poking white thing coming out of the middle of the sunspot. I've not had it very often, but it can happen. And again, from Stuart, this is looking at the difference between hydrogen alpha and calcium K. I like calcium K because it's purple. I don't actually have a calcium K telescope myself, but what they're really good at looking at, I believe visually you can't really see that much, but on images you really see these plage areas, which are obviously very active regions, disruption of the kind of magnetic field within the sun. But also in hydrogen alpha, you get the filaments and prominences as well, which you don't see in calcium K. So it's really good to look at stuff in all of these different wavelengths. Gary Palmer is an amazing solar imager, and this picture is just sensational. I love colour images of the sun, and whenever I sketch the sun, I do it in coloured pastels. But the next picture by Gary is making me want to crack my pencils out so badly and draw this, because it is stunning. The amount of detail in these active regions, I mean, I could talk about this picture for an hour and not get bored. You probably would. So that's beautiful. There was another couple of active regions came into view at the end of December, and I managed to image a couple of them myself, and so did Ella Bryant. This picture again, you can see all the plages around the sunspots, but you also get them where there are no kind of labelled active regions as well. So it's very, very dynamic. Michael Stefan also imaged those regions in white light and in calcium K. Again, just really nice to just compare and contrast the two. And it's fun to draw them as well when you draw the two different lights and see how different those pictures look. Now, my pictures are nowhere near as good as those, but there were quite a few smaller active regions that appeared in the second week of January. Now, as you just heard, I won the BAA prize, the Sir Patrick Moore prize last year, and I used that money to buy a little portable Altaz mount for outreach purposes. I was playing with that and realized that I could get the sun from part of my garden where I can't normally do it from the telescope here, Aurora Observatory. And just by complete coincidence, I was imaging on this day. This picture was taken at 12:38. At 12:36, a solar flare went off just on the limb. It was from a region that hadn't yet been numbered. RPST is quite old, so I'm not getting the contrast that I used to get, but the fact that the first picture I took with the mount I bought with that prize money was a solar flare, I'm really happy with that. I think that's amazing. And those other smaller regions, although they're not as impressive as the previous ones, again, it's just interesting to look at them in white light and H-alpha. And it's hard to see on this picture, but there are actually, there was a huge prominence region just here as well. It's not showing up very well on this screen, but there's been a lot of prominence activity during the week that I was imaging as well. So please do keep those solar observations coming in, and please have a go at drawing it, because drawing's amazing and you learn so much more than taking pictures. Now, obviously closely linked with solar activity is Aurora activity. And from somebody that is an Aurora observer from mid-latitude, again, it has been a long time since we've had any hint of a chance of getting anything from down south. I keep pressing the wrong button. So in November, there were 7 solar storms. So having gone from almost nothing to that is really amazing. And out of that, there were 11 reported Aurora sightings from BAA members. And I'm going to show you some photographs in a minute. In December, there was one R1 class solar storm. I was out imaging all night, but it just didn't reach where we were in North Oxfordshire, and there were no other sightings either. I think the weather was really against us in December. But during January, there were 2 solar storms, and actually this morning my phone went off again, alerting us to some heightened solar activity. So keep an eye on the apps, because we may get something tonight as well. But there were several Aurora sightings coming from that. Now in November, I did get some Aurora pictures from Oxfordshire, but it was just the tiniest hint, so I'm not showing those today. But these pictures that I'm showing you are fantastic. This is Jim Henderson from Aberdeenshire, absolutely beautiful Aurora arc there with the silhouette of a house. It's just so lovely. It's so nice to see this again after so long of not having much going on. Now, this picture will probably be showing up better on the live stream than in here, but this was taken from Swansea, so it's not that different in latitude from where I am. And it just shows that it is actually possible to see aurora from these regions, but it's not going to look like those day glow green pictures that we see on Facebook all the time. It's very often colorless. You can actually see pillars here. There are just a couple of little pillars, and there was definitely a green band there. So if you are mid-latitude, just get your camera out and point it north if there's been an aurora alert. I've picked stuff up from KP6 upwards, but obviously you need a negative BZ for it to be visible this far south. This is from Stuart Baldwin, also in South Wales, and again, this is just beautiful, and you've even got reflection of the aurora in the lake, which is just so pretty, but lots of kind of pillars going on there. And actually above the green, there's a very clear purple band as well, which is different levels of excitation of the molecules in the atmosphere. So very, very beautiful. And finally, Tracy Harty from North Wales, Penryn Bay. This is a really beautiful picture. I bet she was so angry at this band of cloud. I certainly would have been, but it's a really beautiful picture all the same. Just being that bit further north really makes a difference. So yeah, definitely keep an eye on the apps and just give it a try, because quite often, even if you can't see something visually, your camera will pick stuff up. And I personally find that just keep shooting continuously and making a time-lapse video will reveal movement of aurora that you might not have seen on a single shot. So just get a big memory card and just keep shooting, because you never know, you might get something. The Shetland Webcams, Sandra wanted me to let you guys know, I think most of us will be familiar with CliffCam 3, which in the summer is like loads of beautiful seabirds nesting, and in the winter is pointing north for aurora. There are now 2 new webcams, one at the Escherness Lighthouse and one at Borough Firth, and they are both dedicated aurora cameras, further north, pointing north. So if those of you that don't have a good northern horizon or from a latitude that can't possibly see aurora, that would be a good place to go if we see that there is an aurora alert going on. And if you do spot aurora, please let Sandra know. It's really important that we gather this information. Now, also in Sandra's section is noctilucent cloud reports, and currently the Southern Hemisphere are having their noctilucent cloud season, or so they should be. As somebody that is obsessed with noctilucent clouds, I feel so bad for them, because it's been a really slow start this year. Normally it's from mid-November through to about mid-February for those guys. But this year it didn't start until the 14th of December, and even when it did, it really wasn't anything much to write home about. And as far as I'm aware, there still haven't been any actual visual sightings of NLC from down south. And now you rarely get as many sightings down there as we do in the north, simply because there isn't as much land mass with people living on it. But even so, it's really frustrating for those people. Part of this is because the winter conditions in the stratosphere persisted longer than normal. There is this zonal wind that needs to change direction to an easterly direction in order for that kind of summer weather to happen. Noctilucent clouds cannot form if the mesosphere is warmer than minus 120-ish. And that can't happen unless it's warmer lower down, because that brings the cooling air upwards, and it's the opposite way around to where you might think. And so that's part of the reason why. And that wind changed direction on the 13th of December, and the next day some noctilucent clouds started to form. You do also need a source of water, and when the sun's more active, the UV radiation breaks down what little water there is in the mesosphere. So there could be a couple of things happening here. I'm not an expert on stratospheric, mesospheric weather patterns, but I really hope that these guys get a little bit more going on, because noctilucent clouds are amazing. This was from the Ames satellite. It goes around the North Pole when it's our season, around the South Pole when it's their season. This is the most recent picture I could get yesterday, and this was from Tuesday, and there is a little bit more going on now. The picture from the 17th had like 3 little tiny groups on it, so hopefully this is going to pick up, and those guys will get some more sightings. So if any of our members are in the Southern Hemisphere, keep looking and let us know if you see anything. So moving on to the moon, I photographed myself on the 10th of December, a daytime International Space Station transit of the moon. It still blows my mind that with a small refractor and a high frame rate camera, you can pick up the space station against the background sky in daylight. I set up for this not thinking I was going to get anything, because I used transitfinder.com. My laptop said it was going to miss. My phone said it wasn't going to miss. So I didn't know which one it was going to be. So I just did it anyway. And there's this tiny bit of the moon got transited plus the shadow side. But there are kind of 60 images here that had the ISS in them. And it's just incredible that you can do that in the daytime. Not sure how well it'll show up, but just to show how fast this is. Basically, it transits the entire moon in less than a second. I don't know how well that's showing up, but It's a challenging thing to do, honestly. I blog when I'm doing this normally. You can see the stress emanating from my body. And does it matter if I don't get it? Not really, but I think it's a really fun thing to do. It's one of the few satellites I'm not unhappy about seeing. So there we go. On the subject of the ISS, I had to share this tweet because this is hilarious. Obviously, we all know about the huge volcanic eruption that happened in Tonga, and effects of this were photographed from the space station. But apparently, in order to get these pictures, one of the astronauts opened the window. Did they do that on live stream? Because it's something they're only going to do once, which coming from an NASA astronaut's Twitter page is quite a mistake to make. I'm sure they meant open the window blind or cover, but I thought that was really funny, so I had to put that in. But talking about the moon, just to go through what the phases are going to be in the next couple of months, we've got the new moon on the 1st of the month, on the 1st of February, then the first quarter on the 8th, full moon on the 15th, no supermoon as far as I'm aware, and then last quarter on the 23rd of February. These are pictures that I created using the NASA visualization tool, which I'll show you the web address for in a second. It's really good for showing you exactly what the moon is going to look like at any time and date. And then on the 2nd of March, we've got another new moon, and then first quarter again on March the 10th, and then the 18th of March, a full moon, and then last quarter again on the 25th. And I think it's like the 2nd or 3rd of April that we've got another new moon. So one of the things I like to do with that visualization tool is look for when these different clair-obscur effects are going to be visible. I'm sure 2 years ago when I did Sky Notes, I talked about the Lunar X because I'm a bit obsessed with it, to be honest. It's just so sweet. I like many clair-obscur effects, but if you can't see them, the X and the V, these are great for outreach because suddenly there's a letter X and a letter V on the moon, and they kind of show up in the shadowy part of the moon. Up close, these are some pictures that I took, which are not showing up very well on here, but the V is here, but you can see the X there. When you get in close, you can see it's not a solid X at all, because this is just sunlight reflecting off the rims of 4 different craters, and there are little nibbles taken out of it. But it's really interesting to just watch how this forms. And I think this video I created a couple of years ago, where over time, just over 6 hours, I photographed the same part of the moon just to show how, it's going to play once and that's it. But it just shows how quickly the region around the terminator actually changes. I think there's a temptation to just go out, get some pictures of the moon, go back in again. But if you go back out 2 hours later, the whole landscape near the terminator can have changed drastically. And if you've got kind of a sunrise over a crater, the shadows are changing all the time, they're beautiful to sketch. It's worth just spending a few hours in a night just going back to the same regions and seeing how things have changed. Another one that I really like is the face in Albertagnus, and this is visible 2 hours after the lunar X and V are visible, which is on the 8th of February. I forgot to say that before. So the X and the V will be visible about 1700 UT. The face in Albertagnus is visible for a short time, and the shadow you can just make out here, it looks like that's an eye, then there's a nose and a mouth. It's quite creepy, and it's a great example of pareidolia, where the human brain assigns human characteristics to random things. And it is quite weird when you just see this kind of side profile shadow of a face. So that's a really good one to look for. And one more that I really like is the eyes of Clavius. And this is super easy to find because, of course, Clavius is the biggest crater on the near side. And if you get this at 11 o'clock or 2300 UT on February the 9th, you will just see, it's not showing up on the picture, but the 2 craterlets within Clavius, the outer rims are just that little bit higher, and they catch the sunlight before the crater floor, and it looks like these 2 creepy eyes looking out of this shadowy void. And it's another great one for outreach if you can convince people to be up at 11 o'clock, which is a challenge. But it's really worth just, again, looking at that over time and seeing how that crater has changed over the sunlight. So the tool that I use to look for these is the SVS NASA tool, the so-called dialer moon. And this, you can just put in the month, date and time. It only does it down to the nearest hour, but that's usually close enough. And it will show you what the moon looks like at exactly that point. And it's worth bearing in mind that you can do this. It shows the moon as it would be from space. So the moon may not be visible from your location when you find these effects, but those are the ones that are definitely visible from the UK. So that's the moon. I'm going to move on to the planets. And I'm going to talk about a couple of lunar planetary conjunctions in a minute. But first of all, there's been quite a lot of stuff going on Jupiter. There was a convective outbreak in the northern equatorial belt, which is usually a relatively quiet region. And this was imaged by lots of BAA members, and I've got some great images to show you. But by complete coincidence, Juno on Perigove 38 actually kind of flew over and imaged that same region. So on the Juno cam pictures, you can actually see a close-up of the cloud plume that was the result of that outbreak. And you can go and download any of the Juno images yourself and just process them, and it is incredibly good fun because most people from their back garden are not going to get that level of detail on Jupiter, so it's really, really good to go and play with those pictures. Now, Perigove 39 was on the 12th of January, and it imaged exactly the same region again, so it'll be really good to compare the two sets of images, but they've been really slow to come down, so there are no pictures in this from that. But these pictures are taken, they were sent to me by the Jupiter section. You can just see these outbreaks here, these kind of bright regions that were otherwise in a very quiet equatorial belt region. So this is the northern equatorial belt. And these images started to be taken before the Perigove 38 data. So it was really great that they overlapped. And this is just showing the evolution of those regions over different nights by lots of different observers. So again, just shows the importance of having everybody imaging Jupiter at the same time, because you can put this stuff together. If you've got clouds somebody else might not have, and you can build up this really beautiful picture. This is a close-up picture of that cloud plume from Juno cam, and it's so beautiful. Again, makes me want to crack my pastel pad out and do some drawing because that is just gorgeous. So the other picture that we've got here is taken around the 9th and 10th of January, and 5 different Jupiter observers again spotted another outbreak in the northern equatorial belt, and that is Io, the smallest, the nearest orbiting moon around Jupiter, and I think that is Io's shadow. And then over here, we've got one of the other kind of storm regions that's not far from the Great Red Spot. But what's interesting about this picture is if you look, the arrow there, the black arrow, is showing where Juno went on Perigove 39. So it's going to pretty much go right over the top of where that new outbreak is, and the equatorial region being there. So it'll be really interesting to look at those images when they do come down, and it'll be very, very interesting to just compare the two. But it's really important for ground-based people to be looking at Jupiter in this detail and looking for these outbreaks, because Jupiter is not a still world. There's a lot that changes all the time. If you want to find Jupiter tonight, you need to kind of look over in the southwest. It's very low now, but it's still pretty bright, and you will see it low down, kind of west-southwest sort of region. You can't miss it because all the other stars there are quite faint. So that's where Jupiter is. But if we look a little bit further up there, we also have Uranus. I think technically it's just within the realms of naked eye visible, but generally most observers will need binoculars or a small telescope to see it. But you will see it there. Obviously wait till the moon's out of the way, because it will bleach the sky so much that you won't be able to see anything. So this is actually how the sky will look tonight. So if you go out tonight at 6:30, this is kind of where everything will be placed. That was so beautiful, I accidentally put it in twice. Uranus is another world. Obviously, a lot of people can't image this sort of detail on Uranus, but Luigi Marone sent this observation in. And this is showing a really bright region in the northern part of Uranus. It's this kind of outbreak of bright region. I don't understand that much about Uranus, I'm sorry. But you can see that this has been there a while, and this recent observation shows that that new bright region is still visible. So again, these gas giants are not static worlds. There's all these other things going on there. So that is an incredible observation. I can't even comprehend getting a picture of Uranus like that myself. So thank you so much for sending that in. Now, Neptune is also kind of not far from Jupiter. So this is what it will look like at 7 o'clock tonight, so a bit further up in the sky, and there are some kind of constellation lines on there to give you a bit of navigation, so it's kind of just up above Aquarius. So again, Neptune, definitely going to need binoculars or a telescope to spot that. Now, Jupiter is going to be slipping down towards the horizon during February, and by the time we get to the beginning of March, it's heading towards solar conjunction, which means we won't be able to view it because it'll be too near the sun. So solar conjunction is on the 5th of March. And Saturn is also heading towards solar conjunction on the 4th of February, so it's not the best time for the gas giants, unfortunately. And then on the 13th of March, Neptune is also in solar conjunction. So you'll be able to see Neptune during February, but by middle of March, it's going to have slipped down too much and get lost in the solar glare. But you can still spot them if you go out like now. You'll get a look at some of those. If you want a really beautiful conjunction, you can look on the 3rd of February, and a couple of day-old crescent moon will join Jupiter low down in the southwest. I always think that crescent moon and planet conjunctions are really photogenic, especially if you expose long enough to get Earthshine. They're just so pretty. So that'll be a really nice one to look for. Moving over into the dawn sky, if you like being up at 5 to 6, which I do not, but it would be worth getting up because Venus is going to be very low but very, very bright in the coming weeks. And you may, if you've got a very, very clear horizon and no light pollution, you might just get a tiny glimpse of Mars, but Mars is going to be a challenge, to be honest. And Venus and Mars here on the 20th of March. Venus on that date actually will be around about mag minus 4.7. So this is the time of Venus's apparition where people start calling in UFO reports because the people are just not used to seeing Venus looking that bright. But Mars will be just below it. So it is at greatest western elongation on the 20th of March. It's not going to be very high in the sky. You're going to need a low horizon, but you really will not be able to miss it because it's going to be so, so bright. And again, this is Mercury joining the pair. This is going to be a challenge. This is going to be very much near the solar glare, so please don't try this if you don't know what you're doing because don't point binoculars where the sun's about to rise above the horizon. But we've got this lovely triangle of Venus, Mars, and Mercury. This is on the 16th of February, and that is the date Mercury is at greatest western elongation. During March, Mercury is not visible at all. As you can see, it's already pretty close to the sun here. So not the best time for Mars and Mercury, to be honest, but you may just be lucky to catch a little glimpse of them. Another conjunction that I thought was worth mentioning is I think the Hyades cluster doesn't get enough love. I think it's a lovely cluster, and there's a lot of stars in it. You think of it as this little arrowhead, but there's over 100 stars in the Hyades cluster, and it's very pretty. But the moon, when it's almost half full, is going to sit right between the Hyades and the Pleiades, and that is going to be on the 9th of February. So I think that is another photo opportunity, and that's just a really nice alignment. I really like the moon when it's near clusters like that. Another thing to look out for here is the winter Milky Way. And I don't think the winter Milky Way gets enough love either. It's not showing up very well on here, but you can see the band of the Milky Way throughout winter. Obviously, it's nowhere near as impressive or as beautiful as the summer Milky Way, but if you point your binoculars at it, you will just be tripping over yourself with deep sky objects. There are so many clusters, nebulae, so much stuff going on within that band. And there's all the gas and dust and all the background stars. And you can just get lost in it. It's really pretty. And over in the kind of late night, early morning sky in the east. We've now got Leo getting quite high, so you've got galaxy season starting. So while there's not a lot going on in terms of bright stars in that part of the sky, we've got Ursa Major and Leo really high, just again teeming with galaxies, so absolutely loads to choose from. Now, I did take a picture of the winter Milky Way, which is not going to show up very well on this screen. But yes, it's not as impressive, but it just getting that whole arch of the Milky Way going over here from my back garden. I want to do this again because the tree that you can just see behind here got taken out by a tornado on Halloween. There were 11 tornadoes in Oxfordshire and Northamptonshire on the morning of Halloween. One of them went directly over our house. And there is a video on my YouTube channel of that huge tree going down and then us ducking as part of our roof got ripped off. So that one is safe for work. The version on Facebook is not, because it was frankly terrifying. So I've always wanted to see a tornado or a funnel cloud. I no longer ever want to see one again because it was really scary. But I think it'll give me a better outlook on this picture because there's a huge tree gone from our skyline now. So moving on to variable stars, NovaCAS 2021, or V1405 CAS, has been the nova that keeps on giving, quite frankly. So this was discovered in March last year, on the 18th of March. And I remember I actually had a photograph of this from a couple of days before the discovery was announced. And I've got the progenitor star just faintly there, and it did get brighter a couple of days later. But it is still, I love how astronomers say it's quite bright at 10th magnitude. But in astronomical terms, with the equipment that most of us have now, that is definitely achievable. It is fading, and this is the light curve from that variable star. And it's been really interesting. There's loads and loads of peaks and troughs here, and I think the reason for that is it's a very dusty nova. So as dust obscures things, they get dimmer, and then it clears, and they get brighter again. But the trend is now definitely going downwards. But all of these people have contributed to this light curve. And again, it's just so important that when we've got these transient events, that as many people as possible are observing them, photographing them, doing photometry on them, and sending that information in, because it's thanks to people doing that that we can do science like this. So crucially important that we always do that. This is a picture of NovaCAS from the 5th of January by Mike Harlow. His markers were really faint, so I've just added them again here. So this is in a really pretty region of Cassiopeia where you've got the cluster M52 up there, which is lovely, but you may have spotted the Bubble Nebula down there as well. This is such a gorgeous photograph. It's in monochrome. The original is really beautiful. So yeah, that nova is definitely achievable with most people's equipment. So yeah, keep going for that one. On the subject of NovaCAS, Mike Harlow's been doing some excellent spectroscopy using a prism spectroscope that fits on the objective lens. This is incredibly difficult to do. I don't think people appreciate how difficult this is when you've got something that's essentially in the plane of the Milky Way and you have about 8 billion spectra in the same image. But this is really interesting because it's showing loads of emission lines. This is actually NovaCAS's band here. And there's loads of emission lines in helium and hydrogen alpha, hydrogen beta, gamma, delta. There's just so much going on in there. And the original, you can see all of those emission lines. So it's really great if any of you do spectroscopy to follow up with this as well, because it tells us a bit more about what's going on within that nova. Just a couple of days ago, the Astronomer's Telegram reported a possible nova in M31. That's not been confirmed as yet. It may have been this morning, but as of last night, I haven't seen any further confirmation. But it was independently discovered by 2 people on the 15th and 16th of January. I'm sorry, I forgot to write their names down and I can't remember, so apologies for that. But these are pictures taken on the 15th and the 19th of January, and this is the nova that we're talking about. So it has definitely brightened between those two. So this is definitely one to get people imaging and see what develops. It may end up being a really impressive nova, it may not. I believe M31 has something like a dozen novae every year. So this is obviously worthy of an astronomer's telegram, so it may be a bit brighter than some of the others. So yeah, again, just keep reiterating how important it is to just get photometric observations on these things. So moving on to asteroids, you probably will have seen all the excellent news reports about the near-Earth asteroid pass that we had recently. We call it a close pass, but you'll see in a moment it wasn't really that close. But this is asteroid 7482, also known as 1994 PC1. That did a close pass of the Earth on Tuesday, on the 18th of January. This is a 1 kilometre diameter object, and it came within 5 lunar distances. Now, bearing in mind how far away the moon is, that's not that close, really, but, you know, in astronomical terms, I guess it is. But it was actually the brightest near-Earth object pass that we've had in 5 years, so a lot of people were out imaging it. And this excellent photograph here is from Peter Carson. This is 50 lots of 10 seconds showing how quickly that asteroid is moved through that field of view. So it was a pretty fast-moving asteroid with it being that bit nearer. So it's always worth looking out for these because they are fun to do, like the James Webb Telescope. Just seeing these things moving so quickly against the background sky is really good fun. So comets, there are 3 comets of note at the moment. First of all, A1 Leonard, not in the Northern Hemisphere anymore. I'm not at all bitter about how it upped its activity when it left our skies. No, not at all. It's still pretty bright at around mag plus 7. You're going to see a photograph in a minute of what it looked like when it got to the Southern Hemisphere, and I'm not bitter at all. 67P Churyumov-Gerasimenko is still well placed. It's past perihelion now, but at mag plus 9.5, again, still achievable for most people. And how amazing it is to actually get a photograph of this famous comet that had the Rosetta mission that we followed so closely. I'm not showing my picture of it because it's not really worthy of being shown, but the fact I've got a picture of this comet at all is just extraordinary. So that's definitely still worth observing, and it's going to be well placed all month. And we have another comet, 2019 L3 Atlas. It's actually very far away, but it's a really big comet, so that is around about mag plus 9. So again, that is definitely achievable. So this is a picture that Mark and I took of Comet Leonard. We've actually learned to collaborate. I'm not as competitive with him as I used to be. He even had to build me my own pier because we got so competitive. But we've now been collaborating, and we got these nice pictures. And this was really beautifully coloured, and you know, it wasn't the best picture compared to some that I've seen online, but I was still really glad to have got a photograph of it at all. So that was on the 2nd of December. Again, not at all bitter that it was cloudy on the day after that, on the 3rd of December, when this comet was in conjunction with M3. And when I say in conjunction with, I mean really in conjunction with it. Seeing a comet's tail just going through a globular cluster like that, it's just extraordinary. So yeah, this was taken from Morocco. It was clouded out throughout the whole UK as far as I'm aware. But even when it was approaching this object, the pictures that I was seeing online were just amazing. So I do love a deep sky object in conjunction with a comet. I just think it's beautiful. So this is from Ian Sharp, and this is another picture of A1 Leonard taken on the 7th of December. And then this is what Leonard did when it went south. This was taken from Namibia by Alan Tuch, and the structure in this tail was extraordinary. Quite a few people in the Comet Watch group have been doing time lapses of how it kind of had several outbursts and kicked out all these kind of knots of gas and dust. And the way that this tail was evolving every day was just extraordinary. It's like, why couldn't it have just done that a week earlier? I would have been very happy. But it's great that we do have the ability to do these sort of remote images, and those are amazing. This is a picture of Comet 67P from Ian Sharp. Again, this was taken from Spain, and that was on the 7th of December. So this is still a pretty comet, and there are some nice conjunctions coming up that I'll point out. So 67P is currently in Cancer, and it's going to be kind of hanging around that region for the next month or so. So definitely achievable once the moon's out of the way, and it's not really going to move an awful lot against the background sky, so definitely worth looking for. But on the 9th of March, it's going to be really close, so you can't really see it very well, but that's the comet, and down here there's a galaxy, and there are 2 galaxies here, and from the sky live, they are elliptical galaxies, and having a comet sitting within the same field of view of those would be really pretty. I just love a deep sky conjunction with a comet, so that'll be worth looking for. On to Atlas, that is currently in Gemini. and this is how it will be on the 1st of February. And Atlas is also going to have a really nice conjunction with a really beautiful cluster. This is NGC 2266. And as you can even see on this screen, it's got some very colourful stars in this cluster. And I think a comet near this cluster is going to be really, really pretty. So that is the 31st of January. So let's hope for clear skies then, because that's really close to that cluster. So I think that'll be really beautiful. So on to meteors. I've had to pull from our own resources here, so thankfully my husband and I are involved with a couple of different networks. So we've had some really nice meteor showers. The Geminids was the 4th to the 20th of December, as most of you will know. And across the UK meteor network, we had over 9,000 single station detections, which is amazing, but you can't do a lot of science with a single station detection. But of those, 2,700 or so were actually matched events, and that's when you can start doing some science. And from that, we got 962 solved trajectories. And this is important work because it will kind of figure out increasing rates. It will tell you exactly where stuff's come from. It will look for resonances. So it's really interesting to kind of look at that data. I just love getting any meteor regardless of whether it's been matched, but I think from a science perspective, this is great. The brightest that we had was MAG minus 3.99. This is a tracked stack from one of our own meteor cameras, and you can really see that not all, but most of the meteors on this picture are all going the same way. It's really clear that they belong to the same shower. Sporadic meteors will go in any direction. The ones belonging to a shower all seem to originate from the same point, and that is what was happening here with that lovely bright one there. This is from our radio detector, which sadly went offline the last 6 days of December, but it's fairly obvious where the peak of the Geminids was. What you're looking at here is this is every day of the month going down, and this is every hour in a 24-hour period. And each of these numbers is how many meteors per hour were being picked up on our radio meteor detector. Now, this is pointing towards the Graves signal, so this is not all sky by any means, but it really clearly shows that there was a bit of a peak this day, and then on the 14th there was another peak there where we were getting around about 50 meteors per hour. There was another weird spike in activity down here as well. But also the Ursids, while not a particularly impressive shower, you can clearly see the peak of the Ursids here as well on the 21st, I think that was. So these heat maps are really good for a quick glance at when all the activity was happening. We also had the Quadrantids, which can also be an impressive shower. So this one's active from the 28th of December to the 12th of January. And again, a lot of single station detections, over 4,000, which led to 673 solved trajectories. And the brightest Quadrantid that we picked up was MAG minus 2.9, which is very, very bright, very nice indeed. And a much smaller peak than the Geminids, as you'd expect, but this is clearly when the peak of the Quadrantids happened. And that's not offline, we just haven't had the rest of January yet. So these heat maps are really useful because obviously this is able to pick up meteors in the daytime and when it's cloudy, so it's a really good backup for the UK weather that we have in the winter. So this was a random, on the 7th of January, MAG minus 4.34 meteor, which was really bright, and this was picked up at 21:29. This was on one of the stations near Bath. Luckily, we caught that as well, and this turned out to be a Northern Chi Orionid, and this was moving at 23.6 kilometers per second, and the orbit solving of this says that it was probably a Trojan asteroid fragment. So I have a video of this, which hopefully will play. So this was a pretty impressive video to see on our cameras. So really glad to pick those up. So that's the beauty of having these cameras that are recording all the time. So I'm just going to finish up. Those of you that saw me doing Sky Notes in 2020 will remember me kind of voicing my slight concerns over the situation with regards to satellite constellations. Well, things took an unexpected turn on the 15th of November when Russia decided to test their own anti-satellite system by basically blowing up one of their own satellites and creating a stream of debris that has 1,500 traceable pieces of debris, not to mention the ones that aren't traceable. And this has caused all kinds of issues. The Chinese satellite nearly collided with debris from some of that. And when we say close call here, we mean very close. We're talking 14.5 meters. If something like that hits another satellite, you get the Kessler syndrome happening very, very quickly. It's about the only part of the film Gravity that was accurate, I think. But it is a really worrying situation. That is not the way to get rid of a satellite. But then every country is blaming every other country at the moment for stuff that's happening with near misses, because there was an out-of-control Chinese satellite nearly hit the ISS, and actually they had to hide several times in the last month, just get to safety, because there was a probability of being hit. They had to adjust their orbit, and this is a big problem. And then China was berating the US because one of their satellites nearly got hit by a Starlink satellite. And so it's going to go on. And just to give you a scale of where we're at with this, there are now 2,000 Starlinks in orbit. They're chucking 100 up at a time, which is horrifying. The FCC have already approved another 29,500, but there are applications in for 65,000 more. On top of that, I've seen another paper where another company wants to make their own constellation that has over 100,000. This is going to be a major problem, and this is the kind of thing we pick up regularly now on our meteor cameras, where you get these huge streaks from satellites. Luckily, the software is fairly smart and can get rid of them, but from the professional observatories, this is going to be a huge problem. And the IOP, in their journal, there was a study done on the visibility predictions for the mega constellations that had been approved at that time, not even including all the new ones. And this is around 50 degrees latitude, which is where a lot of the professional observatories are. Look how many satellites are visible throughout the night. The ones that are in low Earth orbit tend to be brighter around just after sunset, before sunrise, but the ones that are higher up are visible constantly throughout the whole pass, and they're visible all night long. And yes, stacking algorithms can remove the streak, but that is essentially lost data, and you can't invent lost data. So this is a really worrying precedent that's being set here, and I suspect in years to come, people will look back at this in the same way that they look at us dumping radioactive waste in rivers in times gone by. I don't see how this is going to end well for anybody. So anyway, sorry about that for ending on such a bummer. But yeah, please do look up and keep submitting your observations. And thank you so much for listening, everyone.
Thank you very much, Mary. That's really a fantastic amount of detail you've gone into there. I've prepared Sky Notes in the past, and I know how much work it is. It's hours and days' work, and I can see the detail you've gone into there. It was a huge amount of work, and I'm sure you couldn't all take it all in, even if you were taking notes, but you can watch it again on the YouTube stream. I would say about the satellite constellations, it is obviously a thing that is very much on our radar, on the BAA's radar, and the BAA is part of a group consortium of astronomical societies that is trying to lobby the UK government to do what it can to control satellite mega constellations. Obviously, it's a big international problem. It requires international action. It requires international agreement, but we are trying to get it on the radar of the government of the science and technology ministers. So, although it's a pessimistic thing, it's a thing that astronomy societies are trying to tackle. Any questions for Mary? Yes. Well, no, they've been discussing the weather generally, and also, but they've also been commenting on the quality of the live stream, saying that the sound has been coming across very well and good detail in the photographs. So, well done. I was amused by the anecdote about the International Space Station opening their window. It's obvious why they did that, isn't it? They were complying with COVID guidelines. That's all it was. So thank you very much, Mary, again. So we have to vacate this hall quite soon because they're having some sort of a shindig in here this evening, live music, which they want to set up. But there is a bar here, so you may want to go and hang around there and talk about astronomy. I really would like to thank very much our streaming technician, SL Chai, who has had to do a really difficult job because we discovered that it wasn't possible to link directly to Zoom from the PC on the lectern. So what he was actually doing was actually advancing the slides. He had a separate copy of all the slides on his PC, which was connected to, not Zoom, connected to YouTube. And he was advancing them in coordination with what was happening on the screen, as well as swapping the cameras over and making sure the sound was going. So that was really a complex job. And it all worked out very well. So our next meeting, live meeting, will be in March. Hope to see many of you there. And good observing, clear skies for the rest of the winter and into the spring. Thank you.